certain, or we saw how to name and react aldehydes and ketones, right? So, oh, hold up, I'm not videoing. There we go. We saw how to make aldehydes and ketones using the reactions that you learned in 105 for the most part. We talked about naming them, so we have things in an al for aldehydes. For ketones, they end in -one. The aldehyde prefix name would be formal, and then the ketone one is oxo. Aldehydes take priority over ketones, and that was pretty much it. So, for naming at least. Then we looked at kind of a few basic things. You can hydrate an aldehyde or a ketone for whatever reason. Not a terribly exciting reaction, because it'll just probably snap right back afterwards, except for formaldehyde, I guess. And then we looked at making an acetal or ketal, and how that can be used as a protecting group for your aldehyde or ketone, so that you can react to other functional groups. Remember also that acetal or ketal formation is reversible under acidic conditions, so it's stable against bases, but not stable with acids. So just keep that in mind. If you do conduct a reaction in acidic conditions with an acetal or a ketal, it will revert back to your aldehyde ketone and potentially react. So just keep that in mind. Alrighty, let's look at nitrogen nucleophiles now. So last time we looked at oxygen nucleophiles, right? We looked at water to hydrate things, or an alcohol to put on your acetal or ketal. Nitrogen, we're going to see, we're going to have kind of two ways of reacting, depending if we have a primary or a secondary amine. Or we could have just ammonia as well. So if we take your handy dandy ketone or aldehyde and give it actually, I'm going to write that a little bit differently. It looks weird to me. Yeah, that's a little bit better. So primary one, or it could be ammonia. Either way, if we do that, typically we're doing this in basic or acidic conditions again, and we'll go ahead and see what's going to happen here. We're going to end up making the same thing. I'm sorry, this will be an R group here, and then we have our other R groups. So we'll end up making what's called an imine. So an amine with an A, single bonded nitrogen, and imine has a double bond to nitrogen. And I'm going to just make this super clear that whatever your R group is still stuck on your nitrogen. And so whatever that happens to be, if it's just a hydrogen because you used ammonia, that's going to be a hydrogen. If it's whatever propyl, then it's going to be a propyl group. So a primary amine or ammonia, we'll do this. You'll make an imine when you condense it with your ketone or aldehyde. As always, aldehydes are more reactive. And we're going to see that if we do the same thing but use a secondary amine, meaning that amine has 2 carbon bits on it, here R cannot equal H, for the one on the ammonia. Like, you can definitely have aldehydes. You can have the R groups on your carbonyl compound be H. That's not a problem. Doing this, we're going to get something interesting. And I'm going to actually move this over 1 more carbon for a reason. When you do this, we're going to end up getting what's called an enamine. So we are going to have an alkene being formed as well as our amine, so it's called an enamine. And just to be super clear, it's these R's that cannot be hydrogens. If they were hydrogens, you're just going to make the imine. But if they are not hydrogens, then you're going to make the enamine. So this will be for secondary amines plus your carbonyl compound. So you're going to end up making the enamine this way. All right, let's take a look at the mechanism. And guess what? It's very similar. Let's look at first the imine formation, and then we'll look at the enamine. All right. Yes. An imine versus an enamine, these two? So an imine has a double bonded nitrogen, carbon double bond to nitrogen bond in there. An enamine has a carbon double bonded to carbon that is next to a carbon nitrogen single bond. All right, so it depends where that double bond is. Okay. All right. So yeah, you'll have your let me rewrite this. Plus, we'll say this is a vinyl amine, if that makes sense. So remember, vinyl groups are ones directly attached to double bonded carbons. So you'll have both the double bonded carbon and the amine vinyl on there. All right. So let's look at imine formation. So acidic conditions. Here we go. Let's take a look. First step in our acidic conditions. You can do this with whatever, let's just say HCl, whatever it may be, or we can even use, fine, whatever, HCl. Okay, guess what our first step is in acidic conditions? Protonation. So we're going to activate our carbonyl compound. We lose a chloride, who cares? Whatever acid. I'm just avoiding water right now because guess what? We can hydrolyze these back just like before. So we're going to see we don't want to necessarily put water in here. So using the HCl. Okay, so there's our acid. We've done that. So we've protonated our carbonyl compound. Guess what happens now? Look who's going to come in, but our handy-dandy nucleophile. So now we have this kind of fake. It's not quite a hemiacetal or anything. It's actually called a. Actually, this is. I'm missing a hydrogen, aren't I? We have to deprotonate this first, and then we'll talk about its name. So, like with hemiacetals and stuff, we do have a name for it. So, we're going to go ahead and have our base come back in. I used chloride apparently. Probably not the best base, but here we go. It's going to do it anyway. Again, these are all equilibrium reactions, so I should probably indicate that. Once we deprotonate, that's a positive charge nitrogen. We're going to go to a neutral nitrogen now, and now we have a fun name for this thing. This analog to the hemiacetal is called a carbinolamine. So just another fun, strange word for y'all. So have fun with it. but that's the name of that kind of intermediate. Not really that stable. So we're going to go ahead and keep reacting. So next step. This is kind of, I did this with the acetal as kind of a proton shift, a proton transfer. And here I'm kind of explaining it out. So a base comes back in, deprotonates your amine, and now guess what? The acid is back now, and that has been regenerated. And we're going to go ahead and now use our oxygen's electrons to attack. So we're going to protonate that side of things. H, and then we've got now OH2 positive. And now what's happened is we're actually going to just condense this down. So condense this down, and that's going to kick off our water. I'm going to redraw that, and I'm going to put the lone pair down there so it's a little easier to see. So we come down, we're going to make the double bond here, and we're going to lose our water. See if I can do this. So now we have our positively charged bit here. We just need water or something to come along and grab that. Let's use the Cl minus. Why not? Comes in, grabs the proton. Last step, notice, first step protonation, last step deprotonation. We regenerate our catalyst. So whatever acid we're using, that's what it's going to be. All right, and then we will end up making our product, which is the imine. So it's just like the acetal formation, except we kind of just leave it. We just kind of don't finish it off. We don't attack it with a second nitrogen like we did with the alcohol. We did have an extra alcohol come in. So, and so technically, like, these three steps I kind of combined in one, and you just have your thing attack and kick out your water with the acetal. Here we can't do that because we're going to end right now. We're not adding another nitrogen onto this. So we just make our imine. All right, so that is the mechanism for this. So first, protonate, nucleophilic attack by your amine, deprotonate to make your carbinolamine, or you can just proton transfer. I'm okay if you go straight to this. If you go straight from, I'm going to use a different color. If you go along this green arrow and just indicate the proton transfer, that's fine. I mean, it seems silly. It's like, here's our core, comes and takes out the proton. Okay, now it's going to come and protonate the other thing. Technically, that's what's happening, but it's kind of unnecessary to show that. So you go right here to your one with the protonated water, and then you just deprotonate that, and you're done. All right, so that's how we can make an imine. Of course. So imines are also called Shiftbases for some reason. They're bases. Surprise, surprise. Notice that you can go from the positive charge. Okay, hold on, I'll wait. Sorry, I'm getting ahead of myself here. So, yeah. Let me know when you're good, and we'll look at the next one. Okay, cool. So they're also called Shiftbases after some dude. I'm not really gonna go crazy like this functional group, the imine, is also called a shift base. Not really that exciting. So we'll see that there's a certain type of imine that's very useful synthetically. That's going to be an intermediate in a reduction reaction that we can do under basic conditions. But we'll look at that in a little bit. So for right now, that's just how to make an imine. If we want to do the enamine instead, the process is much the same. So in this case, we're going to be using, and I'm just going to actually just go ahead and just use like cyclohexanone or something. And we're just going to show that this way so you can see where the enamine is formed. So first step, since this is also done under acidic conditions, the lone pairs here. There we go. First step, protonate. Wonderful. Second step, nucleophilic attack, just like before. Wow, that's terrible. I need to draw that lone pair somewhere else. Here we go. Comes in, attacks. And just like before, we end up with this intermediate that has, I guess right now it's just the OH and then the positively charged amine. Technically, base comes in, it'll take it off, and then it'll move it to your water. Is it okay if I do that in one step? Y'all don't got a choice. So with that, I'm just going to move my proton. Be consistent too. Okay. This is exactly the same as what's happening in imine formation, except this is going to be the point of difference here. So notice now we have this positively charged nitrogen, which we can't just take a proton off. In the last case, we had the positively charged nitrogen, and there was a proton, so we could just get rid of it. Right, but we don't have that luxury this time. And so, what's going to happen is we're going to have our base come in now, and we're going to have this get deprotonated. So, typically this one is actually done under basic conditions, but we'll just show it acidic right now, and then I'll show you basic. Here we go. Comes in, grabs a proton off an adjacent carbon, and we're going to end up pushing, or we're going to end up eliminating and pushing the electrons onto the nitrogen there. And so we end up having our enamine. So, why is it this proton? Well, if we look at a resonance structure of this, a resonance structure of this molecule puts a carbocation here. If we just move that double bond up. And so that's the reason that this adjacent proton becomes so acidic, is because now it's adjacent to a carbocation, and so it's ready to go. And so some base will come in and grab it. So that's why this proton is so acidic. All right, and so that's why it's going to be eliminated, and we're going to end up with our enamine. All right, so I'll just leave it on this part right now. Under basic conditions, we can do this as well. So it'll work. Hold on. What about the substitute? Like these R groups? The nucleophile is the amine. In this case, it's a secondary amine. In the first case, it was a primary amine. A primary amine only has one R group on it. So this is the difference here. This is our nucleophile, one R group only. For the enamine, we have two R groups. All right, so yes, this nucleophile is more substituted. Doesn't matter what they are, ethyl groups, methyl groups, whatever. Okay. Okay, cool. I'm gonna erase these. All right, so exciting reactions, as always, right? Let's see. There's a couple of other kind of little bits here. I'm gonna put it up so maybe we can see both at once. So we see here that the mechanism is pretty much identical. Although in the first case we're able to remove a proton, and so we do, so we end up with our imine. And in the latter case, we do not have a proton on our positively charged nitrogen. So what happens is, through resonance, it could form a carbocation next to that proton, or we could just have it attack directly. And so we have our base coming in and grabbing off the water. Actually, it's probably a better idea to just use your amine as the base, now that I think about it. Water is kind of a crappier base. So let's change that. Let's make this a little better. Let's put our same base as before. There are nucleophile. We'll use it as a base now. Be a better base than water would be. So in we go. We end up getting our we'll end up just protonating that, and we'll get our thing. We'll get our product, our enamine. Now we have stronger bases available. Why wouldn't we? And in fact, that can avoid the problem with the chlorine otherwise. Anyway, that doesn't really change anything though, so we'll leave it here. Okay, so those are our kind of our two major nitrogen nucleophiles that we can do with these ketones and aldehydes. And so, see a couple of exciting other cases. If we take our ketone or aldehyde, if we put it with this dude, we'll end up making the following compound, which is called an oxime. So our R group in this case is an OH. That's it. That's the only difference. Mechanism would be exactly the same for imine formation, but it's just got a special name. And then we have another one. This will be an important one for us. This little dude here is called hydrazine. this molecule. It's kind of two ammonias put together. When you end up making is a hydrozone. It's a fun name for the day there. So same thing as imine formation mechanism for all of these, but these have special names. And I put acidic conditions on these. These can all be done in basic conditions as well. So totally acceptable to do that. So we can totally use those. All right, so questions on those. I'll go up and I'll write that. Oh dear, oh dear. We can use basic conditions on these as well. So I've drawn our mechanisms as acidic conditions. You can use basic conditions as well on these things. All right, so with these, we have an interesting other thing we can do with hydrozones, and that is we can just get rid of them. And so we have a cool reaction called the Wolff-Kishner reduction. We just got to put a base with this thing once we've made our hydrozone, and we can get rid of, just get it to leave completely. So it's cool stuff. So let's take a look at it. Why am I even writing hydrozone? Wolff-Kishner. So this will work on hydrozones. Typically, it's just written directly as starting from your ketone or aldehyde. And what ends up happening is you will just get rid of it. So just like how Clemenson was an acidic way of getting rid of a carbonyl, we use that on Friedel-Crafts acylation products to get rid of the carbonyl. Wolff-Kishner reduction does the same thing, but in basic conditions. So you'll use sodium hydroxide to do it. So if we want to take a look at that, first I'm going to just draw it as the hydrozone, and we'll take a look at the mechanism for how this works. We're going to need some. So once you make your hydrozone, we're now going to treat it with strong base, and we're going to go ahead and react it. Okay. So we've got our negatively charged nitrogen now. It does something interesting. It's going to do a little bit of resonance. So our negatively charged nitrogen is going to resonate, and we're going to end up moving a lone pair onto this carbon. And that's just going to end up grabbing a proton off our water. So remember here we lose water. So here we have some water. Go ahead and grab it. Deprotonate. deprotonate the water, I guess, so we're technically protonating our species, but that's okay. All right, and then guess what happens again? That OH now comes back around. The OH that we just made knocks it onto the nitrogen. Already has a lone pair there, by the way. We end up making our same thing as before. We make our negatively charged nitrogen, our conjugate base. And look what happens, same thing as before. End up breaking that single bond. Notice what we lose as a product here. This is an irreversible step because we lose nitrogen gas. So that just bloop, flies away. Notice this is irreversible. I'm not going to put the equilibrium arrows here. We end up making our negatively charged carbon, which will find its friend water. It's going to go ahead and just take that proton off. And so we end up making our we will essentially have replaced those that ketone with 2 hydrogens. So we will have effectively gotten rid of it. All right, I'm gonna ignore that part right now. I'll leave it up here. So we make our hydrozone as we've done before. OH comes around, deprotonates. We have a little bit of resonance happening, forming a negatively charged carbon, which then grabs a proton off water, making the hydroxide again. Hydroxide comes around, deprotonates an additional time. You end up having our negative nitrogen, which condenses down, kicks off nitrogen gas. So this is irreversible, this step. This step is irreversible. The nitrogen gas just floats away, right? It's gone. It's now part of the atmosphere. And then why did I have H3O plus? Sorry, that's just water. And we'll end up making our base again. So in this case, we're under basic conditions. So first step, deprotonate. Last step, protonate. So we're still good on that end. So there we have it. All right. So any questions on this mechanism for the Wolff-Kishner reduction? All right. So good stuff. Turns out that all these things that we've talked about, the acetals or ketals, these imines, and these enamines, by the way, with the enamine, you could get cis or trans, but trans is probably more likely to happen. Just, trans is more stable, so technically you would have the diastereomer there, but we're good. So all these things, if you put them with water and acid, you'll end up hydrolyzing them, so you end up going right back to your ketone or aldehyde that you started with. So all of these reactions, whichever one we're doing, can go backwards. So because all these were reversible, right? Forming these, the reactions forming these, 100% reversible. So the mechanisms for hydrolysis are exactly the opposite of the way that you made them. So if we take a look at imine formation, let's scroll up here. For imine formation, here was our mechanism. We just do the steps in the reverse order. So we protonate our amine, we have water attack, then we proton shift it to the amine, we kick out our amine, we end up closing down the carbonyl, and we lose our proton. So everything happens here in the reverse order. So, instead of this nitrogen dude coming and attacking, that has been kicked out instead. So everything happens in reverse. So it's much the same. Same thing with acetals. You'll end up protonating one of them, you'll have it leave, you'll have water come in and attack and go so forth, and you'll end up making your ketone again. So all of these, it's just the reverse process. So that's it. It's just reverse of what you had originally done to make your molecule. So whatever you did, if you put it with the ethanol and water, you made your acetal or your ketal, put it with water and acid, and you'll just go back to your ketone. So it's super useful that you have these reversible reactions. So you can kind of hide things in certain ways. So, are we okay? Hydrolysis, pretty boring. Just reverse everything you've done before. All these mechanisms that we've learned, just undo them. All right. Exciting stuff. Look at sulfur nucleophiles. Oh. Yep. Yeah, so I mean, all these are technically completely reversible even right now. We technically have water and acid in this, and it can be reversed right now. But we try and force that through equilibrium. We either will try and take out the water somehow, or we'll just put a crap ton of base in there, or of the amine in there, or something, and really force it with equilibrium. So all of these reactions are equilibrium, so they are 100% reversible, and so it's just a matter then of playing with that equilibrium. If you add more of your product, the water, you're going to end up making more reactants, so you'll reverse your reaction. So that's the idea. Okay? So, yeah, let's write that out. Why not? Before we talk about sulfur. Okay, so we remember that I'm going to just do in acetal. Right, so we, just one H2O. If we look at this reaction, it is an equilibrium, just overall. The acid catalyzes this process, and if you remember about catalysis, that how catalysis works is it provides a easier pathway, right, to get to where you need to go. It works the same way in reverse, right? So it's easier to reverse your reaction if your catalyst allows it. And H plus is such a basic catalyst, there's no way for it to say, no, I'm not going to reverse. So if we want to force one way or another, just remember Le Chatelier's. Actually, I don't think there's a circumflex there. We can either, if we remove this, we make more products. If we add this, we make reactants. So it's all about messing with the equilibrium. So if you put a ton of water in there, you're going to force the reaction to go in reverse. So you're going to get your ketone out again, or aldehyde. If you can remove the water using molecular sieves or some other whatever way, sodium sulfate or something, then you'll end up making more products. So just remember Le Chatelier's principle on this. So it's all about if you disturb an equilibrium, how the equilibrium adjusts to fix itself. So that's why. Okay, so since all of these had water as a product, the imines and the enamines and all that, we can just add more water to get the reaction to go in reverse. Okay? We're talking a crap ton of water, so really force it to go back. Okay? Let's look at sulfur nucleophiles. These are very exciting. You're going to see something completely different here that no one ever... Okay, here we go. If you put this is usually done under basic conditions. Guess what you get? This chapter, I feel like it's just the same mechanism over and over and over again. It's exactly the same as making an acetal or a ketal, but instead it's a sulfur instead of an oxygen. So, very exciting stuff. This is called a thioacetal or a thioketal. I'm not going to show the mechanism. It's exactly identical to acetal formation or the ketal formation, right? Much the same. So, but maybe I should, because this is our first time doing it under basic conditions. All right, we'll do it. Okay, this is the last time, though. Okay, so first step with this, our base is going to deprotonate the, actually it's going to deprotonate this dude. And so that's technically the first step. I'm just going to use that as our nucleophile now, if that's okay. Where it comes in, opens it up. Now we've made our H2O, right? We've protonated our hydroxide, so we have H2O. Look who's here now. It's hydroxide. And so if we want to now go ahead and do the next, this is kind of our like or I don't know what this would be called. This would be a thiohemiacetal or a hemithioacetal. I don't know. but it's okay. We don't need to know that. Let's go ahead here. We're going to see that we're going to have a second one of these thio things being generated. Our OH minus comes in and grabs that one. We make another water. That water, though, is going to protonate this one first. Be generating that. So we have this step is the hard step because we have competing reactions. You have just acid base going crazy on that because now we have OH2+. That's a nice, good acid. But we're going to pretend, or it's all equilibrium, right? So it's going back and forth continuously. Now we're going to have our other thiol coming in, and we're going to go ahead and attack, kicking out the water. And we end up with our product. So overall, we still do make one water out of this. We technically made 3, but we used 2 of them. So we still end up making one water. So if you want to reverse this, guess what we do? Tons of water, OH, or water and H+, or OH. Base catalyzed versus acid catalyzed, much the same thing. So the mechanism is very similar here. All right, this is not a terribly exciting thing, but let me show you one more. I'm gonna hold on this mechanism for just a second. And then we'll do another one. I'm sorry, what? We only make one technically, because we end up using 2 of them. So, like this water, like we technically make water in these 3 steps. I'm okay if you don't, because we're gonna end up using it. Like that's the one we make, right? And here's where we use it. And then we make another one here, because we need to deprotonate this sulfur thing twice, right? So that's where we make 2 of them, and both of those are used to protonate something else. So yes, yep. All right. Interesting thing though with these sulfur ones is they do something that is interesting, especially if we make the cyclic version. If you make the cyclic version, oh, that's really ugly. Let me try again. The cyclic one is special. This is different than the normal ketal or acetal that we made before that was cyclic, that we were able to use as a protecting group, and it was great because we could only put it on one spot because it was one molecule instead of 2. What's interesting here, if you put this with hydrogen and Raney nickel, you can get rid of it. It'll go away. Here, let me distinguish here. So it's another way of reducing a carbonyl. We can put on this thioketal and then use Raney nickel and hydrogen gas, and it's gone. So this is another kind of basic way of doing it. So Wolff-Kishner is one way. You use basic conditions to get that to happen. And then you can use your hydrogen and Raney nickel to get rid of it. Same thing as a thioacetal. Or, no, I'm sorry, same thing as a ketal, but with sulfur. Um, remember, a ketal assuming that these R groups are carbons. This one is a thioketal. And in this particular one, this is a thioketal or acetal, thioacetal, either way. Doesn't matter if you're using an aldehyde or a ketone. So okay, so it's just replacing oxygens with sulfurs. What I hate about this chapter is I have to say it for both. So I don't want to just say ketal every time or acetal every time. It's either one, depending on what you start with. Okay. So fun stuff. You can get rid of your thing. You can also do this under acidic conditions. You could put this thing on with acidic conditions as well. So you could totally, no problem. Put it with acidic conditions, get your same product, and then you can do your H2 rainy nickel. And it's gone. So basic or acidic, just like with most of these, you can do either basic or acidic conditions, and you'll get rid of it. All right, so these are useful in that we can get them to happen in either condition. So, okay, so exciting stuff. We now have 3 ways to get rid of a carbonyl. We can do a Clemmensen reduction, uses zinc, mercury, and HCl, gets rid of your carbonyl. You can do a Wolff-Kishner reduction, uses hydrazine and a base. And then now we have either acid or base conditions using this kind of sulfur business, and then rainy nickel with hydrogen, and then you can get rid of it. Okay? So, lots of ways to get rid of them. Here's another one. Yes. All these reductions. Well, those 3 reductions that I just said, yeah, I'll get rid of the carbonyl. We can also reduce it back to an alcohol if we want to, using hydrogen nucleophiles. So either, oops, lithium aluminum hydride or sodium borohydride and some other solvent, you'll end up getting an alcohol on this. Important to know, by the way, that you'll get a racemic mixture with this because we're dealing with a planar carbonyl, right? It's sp2 hybridized. We're basically attacking with H minus. H minus can attack from either side, and so as a result, you'll end up with a racemic mixture of your alcohol. So you can reduce them just like how you could oxidize them to go backwards. You can make a ketone by oxidizing an alcohol. You can make an alcohol by reducing a ketone or an aldehyde. So just essentially the reverse. So nothing terribly special here, but the important part is you do get a racemic mixture. All right, so ketones, aldehydes, not chiral, right? At least not on that carbon because it's sp2. But now we will get a racemic mixture. All right, very exciting. Really what happens, H minus comes in, attacks. Second step, you end up protonating your OH. And that's it. Fine, I'll show it. All right. Here's some H minus source. I'll do it on the aluminum hydride. We'll do it attacks. Opens it up. I'm going to put our green hydrogen. That's the hydride that came in. And then just have some water. Ta-da! And then we'll have our green hydrogen. So we can reduce a ketone or aldehyde down to the alcohol form if we were so inclined, using either of these reducing agents, which you're already familiar with, presumably. So far so good, maybe. I mean, it's very repetitive, this chapter. So let's do some more. Just general nucleophiles. Let's do some carbon nucleophiles now. All right, here is our handy dandy ketone or aldehyde. What shall we put on it? How about a nice Grignard reagent? We've seen this before. Grignards will go ahead and will attack your carbonyl, and you'll end up getting it as the OH as well. So you'll make an alcohol as well as having now attached your carbon nucleophile to what used to be the carbonyl carbon. So very exciting stuff. So same idea. Instead of H minus attacking, it's the phenyl minus attacking, and then step 2, add the water, and you can get that to go. You've seen this before when you first talked about Grignards, I think. So with ketones and aldehydes, you'll just get them to attack, and you'll end up protonating your alcohol afterwards. All right, nothing terribly exciting there, nothing new at least. If you use cyanide as your nucleophile, you do make something that's interesting. This is called a cyanohydrin. That's its name. This is just called an alcohol up there, so no fun names for that. This one's called a cyanohydrin. And there are things we can do with cyanohydrins that we're going to learn later. But we can turn nitriles into all other sorts of stuff. I'm going to do these as kind of like later reactions, ones we're going to learn later, but we can turn this into an amine. Or we can turn it into a carboxylic acid. Or we can turn it into an aldehyde. you can do all sorts of fun stuff with this. So nitriles can be quite useful for us. So you don't need to know these for now. These we'll talk about when we talk about amines. Okay, so don't worry about these right now, but I'm just showing you that this is a useful thing to do. So that can lead us to all sorts of other ways of putting on new functional groups once we have a nitrile on there. So you can totally use these sorts of things with ketones and aldehydes. Alrighty. I actually do have a new reaction for us. Something beyond plain old nucleophilic attack. Are we okay with this? So carbon nucleophiles, so far Grignard, and then a cyanide going on. Very exciting reactions, I'm sure, you can tell. Mechanisms exactly the same as it would be for this lithium aluminum hydride one. You are going to just basically use your nucleophile to attack, and then you're going to protonate your oxygen. In the case of the second one, you technically protonate first, but that's okay. We don't need to worry about that. I'm not going to ask for mechanisms on these ones, because they're pretty boring. Alright, just showing you what things you can do with carbon nucleophiles with these aldehydes and ketones as your electrophiles. Alrighty, here's the new one. The new one. Oops. The Wittig reaction. Now this is an interesting one. We're going to use a special reagent called a phosphonium ylide. We'll talk about that in just a second. But what happens here is we end up replacing our C double bond O with a C double bond C. And we lose we don't lose it, but triphenylphosphine with the carbonyl on it. So we're essentially swapping the two things. This is a metathesis reaction. So we're going to be, we'll take a look at this. So this is overall what's happening, though, is you'll replace your carbonyl with an alkene, essentially. So you're able to now kind of couple things together, which is pretty cool. So let's just take a look at the mechanism for a simple case of this. And I'm going to say we're going to have, we're going to just say we've got our triphenylphosphine. And let's just say we have H's on these because we'll make it easy on ourselves. What happens here is we're going to have essentially a 2+2 cycloaddition. Which is going to end up making us have a 4-carbon or 4-member ring intermediate. So we have this one is our ketone down here, or aldehyde. And we're going to have much the same thing happen. We're going to do now exactly the same arrows that we did before. And we're going to end up making our product. Oops. I forgot the rest of our things on our phosphorus. But But what's interesting here is we will end up making our and we lose or we don't lose it, but that's the byproduct, right? So we end up making our alkene now from our carbonyl. And we're going to look at some of the stereochemistry outcomes with this reaction. We're going to see typically we're going to end up with the Z-alkene, if that's an option. And there are ways to get us to get the E-alkene as well. So we'll look at those. What's interesting is this this reagent here is actually, it kind of more behaves in its resonance form where we have the negative charge on the carbon. And this is what's called an ylid. So it's a positive charge right next to a negative charge. That's what's called an ylid. And we've kind of seen this before with some of the sulfur-oxygen bonds we've seen. Remember that we saw like sulfur trioxide is really not exactly double bonds all the way around. Really, some of them are single bonds, and we ended up 2+ on sulfur. It's the same idea here with the phosphorus and the carbon. And so it's called an ylid. This is called a phosphonium ylid. I could fix this. Phosphonium ylid. And that's why it's going to behave kind of as a nucleophile here. We're going to see that this carbon bond, we could have drawn this another way. We could have drawn it using the ylid form, so you can see the mechanism a little bit more clearly. So oh my gosh, so many freaking phenyl groups. Oh my gosh. It may be more clear for us to see, aha, that's really what's happening. And then this one attacks the positive. So either way you draw it, I'm okay with it. You can draw it with the double bond as your mechanism. But make sure your arrows are going from the double bonded carbon, attacking the carbonyl carbon. And it may be easier for you to remember that by using C, a lone pair on carbon, to attack the carbonyl carbon. Either way of this is fine, and the rest of the mechanism goes the same way. So we still end up now with our we have this still, and then we still will close down the rest of it. We'll still close down the rest, and we'll end up with our product. So either way, so that's why this thing works. So we have this kind of unstable four-membered ring intermediate, and we end up closing it down, kicking out our oxygen, and replacing it with now an alkene. Oh my god, I did freaking pHs. Okay, thank you. Remember, phosphorus has no problem making as many as 5 bonds. Not a problem with phosphorus because it's in period 3. All right. Cool. So let's see this in action. Let's see this with some actual molecules. So let's take methyl ethyl ketone, or just butanone, and let's go ahead and put it with this ylid here. If we want to draw the arrows, we're going to have our double bond attack the carbonyl-carbon, and we're going to go ahead and attack the phosphorus. I don't know why I drew it horizontally. It's a lot easier if we draw it vertically so we can see very clearly what's happening, but that's okay. And I forget my phenyl groups. And we're going to see here that for a couple of reasons, we're going to end up getting the Z alkene when we do this. We close this down, and we end up making the Z alkene. Remember, for easy, we're looking at the higher priority group on each side, whether those are cis to each other or trans to each other. So Z is cis. So we're looking at our kind of highest priority group on the right side, which is the methyl group. Highest priority side on the left side is our ethyl group, so those two will be on the same side. We end up with the Z alkene. Some of that is due to sterics. We have these phenyl groups everywhere that are going to force our smaller group to be closer to them. So we have some steric effects here. With those dark blue lines, we have some potential steric effects. That's going to guide our smaller group up that way. And so as a result, we're going to have the Z alkene being formed. We're going to see also we can kind of tweak this by adding some other stuff to our ylids. If we use something, if our ylid has an electron withdrawing group on it, we can get the E alkene. It's what's called a stabilized Wittig reagent. And let's take a look at what that might look like. The stabilized one might have an ester or something. Something where we can withdraw the electron density. Or we could put a nitro. Yeah, let's go crazy. We like our nitro groups a lot. This stabilizes the ylid, right? Whatever, H. If we stabilize it, we end up getting the E alkene out. If we go ahead and take our same thing as before, our methyl ketone, notice that this thing can resonate. So we could totally resonate this, blah, blah, blah. We're stabilizing it. I'm not going to show the resonance. Y'all know how to do resonance. But that's going to help this stay more as a, it just stabilizes it. In doing so, we'll end up getting our, I'm going to draw this sideways apparently. Wow. This is Getting crazy. Why did I do it sideways? I guess it's good for you to see all these different ways, right? That's my excuse. So it's going to be better for us to put, hold on, I've drawn this the other way. There we go. Better for us to put our electron withdrawing group away. And so as a result, when we close this down, we're going to end up getting our E alkene as a result. Get our E alkene out. It's kind of a terrible example because it's just a hydrogen, but whatever. So you'll end up getting the E alkene if you have a stabilized one. And so we'll take a look at this in some of the other ways to stabilize ylids like this. We'll look at that on Monday. So let's go ahead and we'll push our exam till next Monday. So that would be the 25th. All right, so we're going to push it to there. So it's going to have all of our all of these elimination addition. Those three things we did with the benzenes. And then, oops, you don't need to see the calendar. And then, what did we just do? Aldehydes and ketones. So much the same as before, right? You're going to have some naming stuff, you're going to have some synthesis stuff, you'll have some predict the products, and other good stuff. Okay, so same idea, mechanisms, that was the other good stuff. So that's what we're looking at. So cool. Any questions on that? We're just going to end 5 minutes early today, if that's okay.